Well, this is the first video for Math 116, and I'm going to go over both sections 1.1 and 1.2. If you take a look at Chapter 1, you'll see it is focused heavily on functions. And there's two main pieces, I think, to this topic. One is the function notation, and then the second is the sort of conceptualization of a function, because there's a lot of different ways that you can think about a function. The simplest thing, if you're familiar with this already, that's wonderful. Then some of this won't be new to you. If this is all new to you, then I'll try to move through it in a way that is easier to understand. So the first most basic idea is that when you're graphing in algebra to begin with, a lot of times we graph with x's and y's. The first step in adapting the function or adopting the function notation is just to replace the y with this notation f of x, which stands for a function of x. Okay? And the same thing is true in graphing. In the standard graphing in algebra, we have x and y, and if we adopt the function notation, we'll have x and f of x. It's pretty straightforward. X is the independent variable, y, or f of x, is the dependent variable. And that terminology comes from the fact that x is independent. We pick the x value first, and then we plug it in, and the y value depends on the x. That's why it's called the dependent variable. Okay, so that's the most basic idea for function notation, is just replace the y with this terminology f of x. Okay? And in the same way that we make a table of values for x's and y's, and I'll stick with this same example, 3x plus 1. Then, let's see, if I just pick a couple, right, x values there, and then here y would be 4, 7, and 10. And then we can do the same exact thing with x and f of x. Now, something that you frequently see with the f of x notation that you don't, well, you do actually sometimes see this with the y notation as well. So instead of making up a table of values here, we could say something like f of 1 equals 4, f of 2 equals 7, f of 3 equals 10. Okay? And so we replace the x variable with the particular value of x that we're interested in, and then that gives us the value for the dependent variable. Whether we call it y, whether we call it f of x, doesn't really make a whole lot of difference. Okay? All right. So those are, I think, the most basic ideas for the function notation. For the conceptualization of functions, this is something that's kind of a longer road. We won't get into it too much. When it does come up, I'll try to point it out. So the conceptualization of the concept of a function has to do with what happens beyond the 4 arithmetic operations that we're familiar with, right? Add, subtract, multiply, and divide. You've got adding, and then its opposite is subtracting, okay? And then if you can think of repeated addition as multiplication, right? If you've got 4 plus 4 plus 4, that's 3 times 4, which is 12, okay? Now, surprisingly, or at least I'm frequently surprised by the kinds of really intense arguments that mathematicians sometimes get into about whether or not multiplication is repeated addition. I understand the arguments from mathematicians who say that it is not repeated addition, that it's more of a scaling feature, right? So that if you have, this is 3 times 4, what if you have 3.2 times 4? right? And there are ways to think about that as well. But I think it's really helpful to think of multiplication as repeated addition, and then multiplication has its opposite, which is division. And I use that fraction bar rather than the division symbol because it's less ambiguous, all right? Now, this is where we get, so these are operations, and the addition and the multiplication are commutative. They have a lot of properties. Now, when you extend multiplication, and we get into the same arguments sometimes with mathematicians about whether or not repeated multiplication is the equivalent to an exponent. Okay? I think it's helpful to think of it that way, and exponents have an inverse or an opposite, which is taking a root. So the issue here is that while addition and multiplication, right? So here's 4, this is 3 times 4. 4 times 3 is the same as 3 times 4. Multiplication is commutative, right? And addition is commutative. 5 plus 7 is the same as 7 plus 5. Now when you get into exponents, you no longer have that commutativity, right? 4 to the third is not the same as 3 to the fourth power. And so this is the stage at which you get into operations or functions, okay? And that's really what a function is. It's like an operation, but usually it's more complex, and that commutativity usually doesn't hold up. Okay. Of course, there are exceptions to those general rules. You can have a function that is very simplistic and is also commutative, but in general, that's what's going on with functions conceptually. Okay, it's sort of a step beyond our normal conception of computation. Okay, let's see here. Let's take a look at the exercises in section 1.1. These problems are on page 7 here. Let's see here. Oops. Okay, so here we've got a couple of functions, and we're being asked to find f of 0, f of -1, f of 3, f of 1/2, and then f of x plus 2, and f of x plus h. Okay, so we'll start with problem 2. We've got f of x is equal to 5x squared plus x minus 7. Okay, so if we want to find f of 0, that's pretty straightforward. We plug the 0 in for the x, and we should come out with just -7. There's not a whole lot of work there. Let's see, f of -1. Now notice I put the -1 inside the parentheses there, and that's really important. This is something that I see frequently. People make the mistake, they take their calculator, they go -1 squared, and the calculator tells them that's -1. Well, that is true, because the calculator interprets this as -1 squared, which is -1 times 1, which is -1. What we want to calculate is -1 squared, which is +1. Because this right here is -1 times -1, which is +1. Okay? So that's something, if you're in the habit of doing this, it's going to lead to mistakes, and so I encourage you to either use parentheses or figure out something that will give you a correct answer. Let's see. All right, let's go ahead and finish this up here. Plus -1 minus 7. So this is 5 times 1 minus 1 minus 7. So 5 minus 8 will give us -3. All right. F of 3, 5 times 3 squared plus 3 minus 7 Let's see, 3 minus 7 is negative 4. So that's 45 minus 4, which is 41. F of 1 half, 5 times a half squared plus a half minus 7. Let's see here. So this is going to be 5 times a fourth minus 6 and a half. We can switch to decimals if you want to. I like fractions. I think they're really useful. But in some circumstances, I think it's just a lot easier to use decimals, and this is one of those. The situation where I think I prefer the fractions is where you get into repeating decimals with the thirds, right, and the sixths and the sevenths and so forth. So let's see here. 5 times a fourth, that's 5 over 4, which is 1.25 minus 6 and a half. And let's see, what is that going to give us there? It's going to be, looks like negative 5.25. Okay. And if you call that negative, you can call this also negative 5 and a fourth, or negative 21 over 4. They're all the same number. They're all correct. Okay. Now what I was saying a minute ago about the thirds is that if you come out with something that is 1/3, you can call that 0.3 repeating. But don't call it 0.3. That's something different. That's a different number. Okay? Some people don't think that that's important, but I think it's important because it's not the same number. Okay? These numbers are all the same, so that's why they're all correct. I wouldn't take off full credit if you made this error, but I do think that it's a way to demonstrate that you understand that these two numbers are different from each other. Okay? All right. And if I erase things before you get a chance to see them and think about them, you can always back the video up here. So let's see here. Let's put this problem back up here. 5x squared plus x minus 7. Okay. So now we get up to the algebraic substitutions that we want to make here. So if f of x is going to be this, then f of x plus 2 is going to be 5 times x plus 2 squared plus x plus 2 minus 7. So all we have to do is take what's in the parentheses, put it wherever you see an x, or wherever you see the independent variable, whatever that happens to be. In a lot of the sciences, the independent variable is t for time. Okay, so let's go ahead and square this. This will be, now don't forget, if you're going to square x plus 2, that means multiply it by itself. That means you're going to get x squared plus 2x, and then plus 4. Okay? The reason why you can't distribute that exponent into the parentheses has to do with the relationship between these forms of computation. Because multiplication can be thought of as repeated addition, that's what allows you to distribute the multiplication across addition or subtraction. Same thing with exponents. Exponents can be thought of as repeated multiplication, and that relationship allows you to distribute an exponent across multiplication, right? If I had something like, let's say 5x squared, that would be 25x squared. I do square root each of them, but that's because I'm distributing it across a multiplication. Here, with this addition, you can't distribute that because you're jumping 2 levels of computation. Okay, so we're going to get the x squared plus 4x plus 4 in there. And then this will be x minus 5, right? The positive 2 and the negative 7 will make negative 5. So 5x squared, 20x, and 20. And then we'll add in those last 2 like terms. Let's see, 21x, and then 20 minus 5, positive 15. Okay, so there's the first one, and then the second one is similar. Let's see here, f of x plus h, 5 times x plus h squared, x plus h minus 7. All right, So 5 times x squared, 2xh plus h squared. And let's see, so 5x squared, 10xh, 5h squared. And it doesn't look like we've got a whole lot of like terms here. And so everything's just going to stay the way that it is. We can't combine any of these like terms here, and so we'll just leave that the way that it is. Okay. So this x plus h thing, this comes from calculus. And the basis of calculus is to look at what's happening to a function at a particular value of x right there, and then shift it over just a little bit, and then work with these 2 points and see what happens as they get closer and closer together. And that's sort of the essence of most of what's called differential calculus. Okay? We won't do a whole lot with it, but I thought I'd throw it in here and just mention that in case you're interested in going on to calculus. All right, so that's problem 2. Let's take a look at problem 4. Let's see here. Problem 4. F of x is x plus 3 over x squared plus 1. Okay, let's see here. So first off, f of 0. 0 plus 3 over 0 squared plus 1. So that's 3 over 1, which is 3. F of negative 1. Negative 1 plus 3, negative 1 squared plus 1. So that's 2 on top, 1 plus 1 is 2 on the bottom, and so our answer simplifies to 1. F of 3, 3 plus 3 on top, 3 squared plus 1 on the bottom. And so if you're going to leave it as a fraction, do reduce your fraction, 3/5. If you want to call it a decimal, you can call it 0.6. These are both correct. The 6/10 is a little bit, I mark a little bit off for unreduced fractions. And then f of 1/2, let's see here, 1/2 plus 3 over 1/2 squared plus 1. So let's see here. 3.5 on top, 1/4 plus 1 is going to be 1.25. So there's a variety of things that you can do with this, okay? I mean, you can do it on the calculator in the first place. And now if you do it on the calculator in the first place, you really have to be careful about working with fractions on the calculator. So let me go ahead and simplify this, and then I'll go back and talk about using the calculator with fractions. So if we just go 3.5, right, the fraction bar means divided by. That's why I use it in place of the divided by symbol. And what do we get out of this? 2.8. Great. Excuse me. Okay, so there's that. What else can we do here? I mean, you can reduce it yourself by thinking of this as 350 over 125, right? Multiply the top and the bottom by 100, and then you can just reduce this. Let's see here. 25 is going to go into this one, 4, 8, 12, looks like 14 times, and then 25 goes into that one 5 times. So 14 over 5 is also a good answer, and I think if you do 14 divided by 5, you'll see that you also get 2.8. Okay. Now, before I leave off on this, let me talk briefly about using the calculator with fractions. So if you wanted to do this on the calculator, 1/2 plus 3 divided by 1/2, well, let me write it out like it appears on the calculator. 1/2 like that. And So the problem with this is if this is all you type in, you're going to get an incorrect answer, because what it's going to do is it's going to do a half, and then it's going to do 3 divided by 1/4, and then it's going to add 1. And so you would get 1/2, 3 divided by 1/4 is, what is that, 12 plus 1, and so this is 13.5. You can see that's not the correct answer. If you want to do this all at once on a calculator, you'll need parentheses. You'll need parentheses here, you'll need parentheses here, and the same thing with the 1/2. You'll need parentheses around the 1/2 if you want to square it correctly. And so I'm often in the habit of just calculating this separately, and then dividing, and then I come out with this, and you can just divide these, and it's pretty straightforward, okay? But if you're in the habit of inputting all of this all at once, be very careful about where your numerator is and where your denominator is, and delineate those with parentheses. Okay. Let's see here. Oh, now we've got the algebraic ones. So, let's see. First off, f of x plus 2 is going to be x plus 2 plus 3 over x plus 2 squared plus 1. So this will be x plus 5 on top. This will be x squared plus 4x plus 4 plus 1 on the bottom. And so I'll just erase that and call it plus 5. Let's see here. I don't think this reduces. This bottom one looks like it might be factorable, but it's not. Okay? And so that is lowest terms for that algebraic fraction. Okay, let's see here. F of x plus h plus 3 on top, x plus h squared plus 1 on the bottom. And this one, again, we get the x squared, 2xh plus h squared plus 1, and none of that reduces, and so we can just leave it like that. Okay. With this one, frequently, it's easier, if there's nothing, if it doesn't simplify, it's easier just to leave it like this. Now here, at least we had some like terms that we could combine with each other, so this ended up being a little bit more neat than this answer was. So in doing these on quizzes and on the midterm and final, I will ask that you simplify everything. Having said that, occasionally it is useful just to leave things in their original form. Okay. All right. So I think that's it for section 1.1. Let's go on and talk about section 1.2. Okay, section 1.2, and these problems are on page 10, and these have to do with what are called domain and range. X's and Y's, okay? Domain are the X's, range are the Y's, or the f of X's. These are the independent variable, these are the dependent variable. These are all just different names for the same things, okay? I've always remembered this alphabetically. X comes before Y, D comes before R, so domain is the X's, range is the Y's. If you ever get a hold of a really old math textbooks, you might sometimes see this note, this language, abscissa and ordinate. Again, 2 more names for the X's and Y's. We won't get into this. I haven't seen this in a couple of decades, but it used to be common language in math textbooks. And again, it's also alphabetical. The abscissas are the X's, the ordinates are the Y's, A comes before O, X comes before Y. Same thing with the D and the R, and the X and the Y. Okay, Now the primary issues here, we'll do some of these where we have graphs and we just want to pick out x and y values. The primary issues that you run into with restrictions on the domain and range have to do with square roots and also fractions. Okay, so those are the two examples that I've got in the problems here. Problem 2, we're saying f of x is square root of 3x minus 5. Now, what a lot of textbooks make a big deal about here is that if you get a negative under a square root, it's going to give you a complex valued answer. Okay? When we do our graphing for x's and y's or f of x, okay, the x's are real numbers. This is the mathematical symbol for a real number. Okay, is that double-barred R. The y's are also real numbers. So if we generate a complex number out of this function, there's no place to graph it. Okay, there's actually some really interesting stuff with complex graphing that we talk about some in Math 111. We won't get into it too much here. It's actually it's kind of a new thing that has to do with computer graphics. People before couldn't graph complex functions before, but now with the more sophisticated computer graphics, people have started to do that. We're going to limit ourselves to what are called real valued functions, okay? And so that's why a lot of textbooks get into this issue of if you get a negative number under here, your y value will be complex, and we can't graph that then. So the restriction here is that 3x minus 5 has to be greater than or equal to 0. It has to be a positive number or a 0. And so we'll solve this, x greater than 5/3. That's our domain. Okay. The range is going to be y has to be greater than 0. Okay. So that when x is 5/3, y will be 0 at that point. Okay? And I think if we graph this, it's going to come out looking something like this. Now you might say to yourself, well, what about the negative square roots, right? Let's see here. What if we put in, let's see, what could we put in here for x? 2. That's a pretty simple one. F of 2 is going to be the square root of 1. Okay? And so there's 5/3. 2 is going to be right here. There's the 1. Well, isn't negative 1 also a square root here? Well, yes, it is. Okay? However, what happens here is that this is something that I think is a convention in American mathematics, is that if there is no symbol in front of the square root, that means only the positive square root and not the negative. Okay? I'm not sure what the reason for that is. I think it's to avoid a certain amount of ambiguity, but there's plenty of ambiguity around that we leave in mathematics. I'm not sure why people felt the need to eliminate this ambiguity. Okay, if you have if you have a function with a square root in particular, then you will only get the top half or bottom half of it, depending on whether this has nothing in front of it. If it has a negative in front, then you just end up with the bottom section of it. All we're really interested in here is the domain and range. So this is why there's a restriction on the y values, is because we're only interested in the positive square roots, and that's why the y's are all positive numbers. Okay? All right, let's look at problem 4. And the concepts that we're talking about here, as I don't know if you're getting this impression or not, but they do kind of go beyond what I'm addressing in the textbook. If you're interested in that, if you have questions about it, if you want to talk about it, I'd be happy to discuss it with you. The things that I'm focusing on in the textbook are simply answering these questions, and that will give you a basic understanding of the concepts of domain and range. All right, problem 4, we've got f of x is x plus 2 over 2x minus 3. So the issue here is a zero denominator. Okay, that's the issue to watch out for here. So if 2x minus 3 were equal to 0, then x would be 1.5. So that means our domain is just x cannot be 1.5. It can be any other number besides 1.5. The range, now this gets a little bit trickier. This will take on most y values, except there is a horizontal asymptote at 1/2. And so I would recommend graphing this. Let's see here. So if we go ahead and graph this, and again, we need parentheses if you're going to graph this. Parentheses x plus 2 divided by parentheses 2x minus 3. Okay, now we'll look at this in the standard window. It's kind of hard to see exactly what's going on there. Here, let me bring this up so you can take a look at it. Now, it's hard to see what's happening there, but this one over here is headed out in this direction as the x's are getting larger and larger. Over here, the x's are getting smaller and smaller. And let's see. Oh, before I leave off on this, let me show you what the table looks like. Okay. So you can see here that as that x gets bigger and bigger and bigger, these y values are coming down, 0.6, 0.5, and so on. But this is never going to get smaller than 0.5. You know, I can hold this for quite a long time, and it'll never get less than 0.5. Okay? So let's go back to the board and talk about why that is. And the same thing, we'd see the same thing in the negatives. If I went up into the negatives, here, let me draw this. Where are we? We've got an asymptote at 1.5 there. So it's doing that. And then let's see. Where is this going to be equal to 0? Negative 2. And then it's going to do that. Okay? It's kind of hard to see just from the graph that we've got this restriction that y can't be 1/2. Why not? Well, let's plug some big numbers in here for x. Okay? Let's say x was 100. So f of 100 is 102 on top, and 200 minus 3, 197 on the bottom. Okay? And we can divide those. Well, I'll go ahead and do that. This is probably going to be a little bit more than 1/2. What do we got? 0.5177. What if we did f of 1,000? F of 1,000. 1,002 over 2,000 minus 3. Okay, so 1,002 divided by 1997, 0.501. Okay, the bigger the x gets, the less important this 3 and this 2 are going to be. Okay, if I made it 1,000,000, it'd be 1,000,002. And then the bottom would be 999,997. It would get closer and closer and closer to 1/2. The bigger the x's get, the less important these get. And you can see there's the 1/2 right there. 1x over 2x is going to give you the 1/2. So that one's a little bit tricky. But again, I wouldn't worry about it too much. And like I said before, if you have questions about these, I'll be happy to talk to you about them in some more detail. All right. Now on the graph, these are a little bit simpler. Now we should assume that these points are on whole numbers, and so for we want to do the even one. Problem 6 on page 11. Let's see here. What have we got? We've got a graph that looks something like this, where this point is 2, 6. Let's see if I can do a better one here. Okay, 2, 6. There we go. A little bit better. And that one is negative 12, positive 13. Okay. So here, our domain is the x values. The x's go from negative 12 up to positive 2. You can write it like this if you want. If you've gotten used to interval notation, then we can go ahead and use the interval notation as well. You only have to do one of these. Either one is correct. Okay. Let's see here. Now the y values, the biggest y we've got is 13. Okay? But the smallest y is not over here. The smallest y is down here. And we've got to take a look at it and estimate. It looks like that's about negative 3. So our range here is going to be negative 3, less than or equal to y, less than 13, or in interval notation, negative 3 up to 13 inclusive. All right. Let's see here. And then we'll look at problem number 8. And that should do it for this assignment. Like I said, this is just kind of an introduction to these function notation and the concept of a function. And I mentioned before, there's a lot more that goes into this, but we're just kind of focused on some of these introductory ideas. All right, let's see here. So we've got something that looks like this, and then this one's down here, and then we've got this one here. Oh, that's an open circle. Okay. So let's see here. The x's to the furthest left, that looks like negative 9. All the x's are included up to, but not including 6, right? So that if we wanted to write this domain, we would include negative 9, but then not put the equals to for the 6, right? And if we used interval notation, we would use a bracket on the 9 and a parenthesis on the 6. All right, the range, the y values, let's see here. Well, the smallest y value is 0. And then what's the biggest y value? Again, it's not inclusive. It goes up to 10, but doesn't include 10. And so again, if we did the interval notation, we'd have a bracket there and a parenthesis there. Okay, so those are the basic ideas for functions. We'll continue to work our way through chapter 1. We'll talk about a variety of other things that we can do with functions. And then at the end of chapter 1, we've got a lot of applications for functions and maximum and minimum values. And that is a preview of something that is typically taught in a calculus course. And so we'll get to that in the next couple weeks. As always, if you have any questions, please email me. You can call me on the phone. I'm in my office pretty much every day. So if you want to come by, just let me know. But if you have questions, ask, and let's try to get any questions that you do have answered. Thanks.